My name is Hüseyin and I work as senior software engineer in Hazelcast. We build a software as a service on top of this Hazelcast technology in memory data grid. Within this session, I will try to explain you what is the Raft Consensus stuff. And this will be mostly related to distributed systems. And at the end of the session, I will provide some sample code base written in Kotlin for this Raft. And if you have any kind of question, you can just you can disturb me, and I can do my best. So, what is Raft? This distributed consensus stuff, the term, is very popular in the distributed systems. So this topic coming from the 80s, there is already a way to do this, which is called, the technology is called the Praxis, but the Raft is for simplifying this algorithm, right? And the Raft mainly solves two problems: the replicated replicated logs and the fault tolerance. You will see whenever you send some data into this environment, the data will be replicated through the members. Raft will provide a guarantee for this. And also you will see this cluster, these nodes will be fault tolerant. Let's go into detail a bit more. So you will see this term state machine within this Raft consensus stuff because there is a client-server interaction. Whenever a client sends something to server side, I am saying something because Raft provides a very abstract way of implementation of this. You need to implement the actual business logic there. So client sends something to server side, and the state machine of the server side can be changed in the different states. So it can be, it can go from A to B, then B to C. Even it can go C to C. Let's say that it is retrying something. So this is a picture of a typical node. But when you think about cluster, because distributed environment, distributed systems are formed by a different kind of nodes, right? So we said state machine, but this time you can think there is a group of servers, and this time we are calling this replicated state machine. The same stuff exists in every node, but here you see there are a couple of modules: the consensus module, state machine, and the log. Let's have a look. What are they for? First of all, client sends some data to the server. Let's say that we have a key value database, and the client tries to send the key value pair to server in order to save them into system so that it will be available through all the servers. When you send this request, actually the data, you can say that the log, I am not saying that data, it is log, it can be anything. And this will be stored in the log. And you see the initial request is initial request made to the leader part. So let's say that this service is the leader. The leader saved this one into its log, is temporarily put this one into state machine, on state machine, and it start to send an RPC call to other servers. So you will see the same operation. Consensus model will be called from the leader via RPC, and then it will be saved in the log. The same command, same log will be saved in the log of the server, the middle server. And then it will store this data into state machine. And same thing will happen for the third server. Then once it get the response from the majority by the leader, it will commit the data. So think about that. This is something like transactional operation. So it sends this request via RPC, get the response from majority, and returns to the client with some kind of response. Let's say that commit ID or data or some response saying that succeeded. So when you so this Paxos was very hard to understand because the problem is big. So what Raft started to do that is decompose the problem into three categories. The first section of the problem is leader election, and there can be only one leader at a time within this cluster. And once the leader crashes, then the system should reselect a new leader. That is the main idea. And the log replication, a client sends data to leader, but somehow this data should be replicated to other members because the other members, followers, are typical featured leaders. That's why the data should be replicated to other members. And So here, the safety, of course, this is very important. The consistency of logs is very important, because when you write data into some node, and if you try to read data from another node, it is outdated. So that is a nonsense, right? This part, consistency of logs, is provided by the Raft implementation itself. And let's say that there's a crash on the leader side, and any member, any follower can be a leader. So you need to have up-to-date logs for this. If you have outdated logs, you cannot be a leader. Let's say that there will be a network partition happen within the cluster network, and then you act like, oh, there is no leader, I need to be a leader. And then maybe you can select yourself as a leader, but at the end, you will have less logs than the other ones, because there has been a network partition happened. So you cannot just become a leader if you don't have an up-to-date log in your system. So let's have a look at the state of the servers. Well, a typical one. Think about only one physical server. Here, you start with the follower. When you start your node, cluster node, it will be a passive state, and typically it will be a follower. And a typical follower expects a heartbeat from the leader. If there is no heartbeat message from leader, this follower starts to think, oh, there is a problem with the leader. I may be leader, next leader. Then it just say that, okay, I am the candidate. Then there can be a couple of more situations here. So here, if you want to switch to a candidate and then follow a leader state, you need to send a request with RPC. So there is a selection, you just decide, and you need to request vote from other cluster members. You can do that. And then if there is a higher term, let's say that you just wanted to become a leader, but there is a network partition error. Then you may have outdated logs. Then somebody says that, oh, I have higher term than you. Then you cannot become a leader. So you just go back to the follower state. But if it is succeeded, you can win the election. What does winning an election means? You just send a request with RPC to cluster members. If you get the majority, then you can become a leader. When you became a leader, then you started to send append entries, RPCs, to other members. So these append entries, let's say that this is a function for synchronizing the data from leader to other followers. But so you are sending data, right? What are you thinking about this? Think about an RPC call. There can be a body data in the payload, but if there is no data in the payload, it is a typical heartbeat message to the followers. So there is no method for heartbeat, dedicated method for heartbeat. So heartbeat and the replicating data is handled within the append entries RPC. So of course, Raft does not provide you an implementation. So there is implementation for this in Golang, different kind of languages. They are already implemented within this way. Okay, so think about the consensus. You are doing some kind of elections, you are doing some operations. They are a typical logs, right? Think about this. What will be the identifier of these operations? You can use time, but think about different kind of time zones. There can be time problem. You need to be very well synchronized between the servers in order to not have a clock problem, because we are talking about the milliseconds here. So they did say that, okay, we shouldn't use time within this design. Let's use a term. So term is something like, well, let's say that they counted a number. It is incremented by 1 on every operation. And the operation means the selection. There can be a failed selection, something like this. But here, think about the boxes right now. The term 1, term 2, term 3, term 5, it goes to some number. And you see the blue parts are the elections. So I just started from the term 1. There is a time reserved for election part. Once the leader elected, then they can do some data manipulation operations. You see in term 2, the election part is a bit low because most probably there is no network error. Then they can just quickly become a leader. And you see in the green area, they are the normal operation. Normal operation means you send heartbeat messages, you send some data to the other team members. So that is very normal operation. But what about term 4? you just try to become a leader. There was a selection, but nobody selected as a leader. So that's why we see a blue box here, but you need to retry because selecting a leader is very important because otherwise it will be a single point of failure. Your client should be connected to leader in order to do a right operation. So first rule is just get the leader up and running as soon as possible. And after turn 4, you just retry the election and somebody became a candidate and then they said request vote. And when they get the majority from the majority, then it became a leader. Then continue with the normal operation. So the logic seems very simple, right? I mean, they are all typical election, and elections are triggered by a very bad situation. So think about it is very same with our normal human world, right? If there is something happen bad, then you just start to think about a new election. Okay. So here in the leader election part, this is the first problem that Raft solves in this context. When you become a candidate, so as you are saying that I can be the leader, I became a candidate, fine. What you do, you just increment the current term by 1. And firstly, you just vote for yourself. So whenever you become a candidate, at the beginning, you will have only 1 vote. Then you can perform a request vote RPC to others. So you may ask that, Hüseyin, what is the others? How can I know servers? Raft doesn't provide the detail for this. So you need to implement this part to provide these IP addresses, host names, maybe discovery systems to this part. You need to implement that logic. So Raft doesn't care about what will be the way of getting this list of IP addresses or domains. And then when you send the request vote, you may not get some response. That means it can be timed out. Okay, it is not a problem. Increment your term by 1 again, provide the vote for yourself. Then this time there is no timeout. Let's say that option 2. If you got the votes from the majority, so what does the majority means? You can calculate it something like this. Let's say that you have 5 nodes within your cluster. You can add 1 to this count, which is 6. And then you can divide it by 2, 3. So within a 5-membered cluster, if you get the majority, that means if you get a response, successful response from 3 nodes, then you can become a leader. So this is the simple calculation. But if you receive a RPC from leader, so let's say that there was a problem on the leader, there was a network problem, and you just try to become a leader, you send your votes, but at the same time, you just get some message from one of the leaders, and then you just decommission yourself to the followers then. So here, we are trying to decide on something by looking at the term numbers. You see, receive RPC from leader. So if there is a heartbeat, that means there is a leader. Maybe you misunderstand the case. So there is a leader there, there's a network problem, but as a follower, you cannot get the heartbeat message because there's a network problem. Then you may think that, oh, there is no leader, but actually the leader is there and the system is working, but you misunderstood this case. So there can be at most 1 leader per term. So within a typical term, you cannot see multiple leaders. So a leader X lives in the term 1. If you elect another leader, that means you need to increment your term. That means you cannot have multiple leaders in 1 term. That is the rule. You send request vote, and then every server's followers provide a vote to you. So for a specific term, there should be only 1 vote per server. So 1 server cannot provide multiple votes within the same term. Timeout should be random. This is a very tricky and critical part, I can say that. So think about you have 10 members within the cluster. If you have same timeout value, let's say that 100 milliseconds. If you do that, if they cannot reach to leader after 100 milliseconds, they will try to just promote themselves to the candidate at the same time. So this situation will provide some kind of inconsistency. Instead of doing that, what you can do is just provide your area, I mean the interval. Let's say that my timeout value will be from 100 milliseconds up to the 300 milliseconds. And then every node decide on some random timeout value based on some utility function, let's say that. So it will have a good design on this part, because when one of them just does not get any kind of heartbeat from leader, then randomly one of them will try to become a candidate, not all of them at the same time. So I am trying to understand. Okay, there is a how Quartum works. I think I already provided this one. So there is a simple calculation. How do you determine the time of the leader election when some other messages comes in telling you I am the leader, that this message is not forged and attacked on the time system integrity? The leader time election, actually, it is handled by this random timeout. So other than that, there cannot be some kind of leader selection, but nobody can say I am the leader. So the integrity comes from something like this. You have one code base, right? And then you deploy same code base, same binary, same whatever it is into servers. So they are same package. So all logic is same between the servers. So you cannot get this kind of situation. Nobody will say I am the leader. But of course, there can be something like this. There are a cluster, that are a set of class members inside the cluster. You can just do a manual RPC call to this cluster saying that I am leader. Of course, you can fake the cluster, but that situation are edge cases. I don't have any kind of solution to that. Maybe you can put some protection layer, but it will introduce a latency. If the cluster is within the private network, and there will be no problem. So you have an average broadcast time. So you send request, vote RPC, you send heartbeat, something like this. Most probably you have an average value. Let's say that 100 milliseconds. So you need to decide on timeout value based on this. If you make your timeout value 50 milliseconds, it will be better, right? Because your average connectivity between the members is 100 milliseconds, but your timeout is 50 milliseconds. That it means even there is no problem in the leader, you will try to send become a candidate on this situation. In normal operation means there is no problem. So there is a term and the leader is alive. What happens in this situation in a typical server? Client sends a command to leader. So client knows how to connect a leader. I will show the example of that. And then let's say that put a value into key, into map with the key 5, for example, the typical map implementation. Leader appends command to its log. So this log is important, and this is a typical file system technology. Let's say that if you are using, you can use Bolt DB in order to maintain your logs, right? And then leader send append entries RPC to the followers. So it gets the data, put into log, and then distribute this, synchronize this, or replicate this message to the followers. And then once it gets acknowledged from the majority, so it gets a response from the majority, as we described on the previous section, it commits this request to its state machine. That is very simple. There is a log, there is a state machine. Let's say that transaction start and transaction commit, something like this. And then right after it commits into its state machine, you cannot override it. So leader knows everything, and right after commit this data into state machine, there is no way to update it. Leader notifies follower committed entries, subsequent append entries, because let's say that you just committed something and there is also a commit index. It is just replicating this message to the followers. Let's say that there can be a new follower just joined to the system, then they will be aware of this operation. And append entries consistency introduced by the index and term. So if you want to write some data, you need to provide those two critical fields for this data. And I just wanted to show you a couple of use cases. What happens? So think about the success, very sunny day scenario. Leader gets some new data from the client. You see the green part the part that already committed. So they are committed, they are stable, no problem. And then leader gets 2 more data from the client. It stores its log, and then it does not commit it to state machine yet. So it sends to the followers. Think about follower at time t. They already have data. You see the yellow one. Follower has this data already. So this blue one should be the third index, should be committed to follower at time 2, right? So this is very simple. It just gets the data and appends it to the on log and then store it to the state machine. This is the success scenario, but there are the complicated ones. Think about this. Again, leader has same data. Now it gets 2 more new data. It tries to save this data into follower at time t. You see, the data is mismatched. Somehow the follower gets some more data from someplace. I don't know, there can be some inconsistency. So there is a mismatch. And then what leader does at this time, just decrement the term by 1 and then try to append entries again. So you see, think about this was the current one, current index, the 2. There is a mismatch, an increment by 1, and it will be the 1, and Q is 6. And yeah, this time is matched, and it retries this one. So leader's responsibility is to convince followers for this data. And in order to do that, it does a typical retry until the follower accepts its request. So it is a typical override operation. So there is a mismatch here, and it retries again with the term decreased by 1. Then you see it totally overwrites the follower logs. That is the state machine. And the final one will be something like this. You see, it is overwritten by the leader. So of course, we always trust on the leaders, but once an entry is committed, it should be stored for all of the feature leaders. So I save the data in my committed data. If I crash as a leader and then the new one is selected, they should have the same log. So it is very important. Then that is why we are storing this last term and last index within the system, so that once the leader candidate try to become a leader, they need to verify that your last term and last index is capable to do that. So that was all with the theoretical informations. I just wanted to show you an example in a Kotlin implementation. If you have questions, I can happily answer them. Jonas Frank just asked something. Does that mean that K9 and C4 are lost? Yeah, it can be. No, there is no loss. Actually, think about this. Somebody tried to become a leader. Let me open that part here. So somebody tried to become a leader, right? And then they send just wrong data. It can be a temporary leader, by the way. They just send maybe wrong data. The network partition, send the wrong data, and they just try to commit this one into on log follower. Then the real leader just enter into the state, then they just overwrite the wrong data. So it is not a lost, but it is caused by an inconsistent leader selection. It can happen anytime. Of course, we don't expect this kind of situation very frequently within a healthy environment. So, any other theoretical question? So this part is Raft GitHub, this one. So this is your original source of truth. I mean, everything is here. You can even play with this demo part. So you see one of them, this server 5 is timeout and try to get vote from the majority, and most probably it became a leader and it started to set heartbeat to the followers. So you can play with the numbers and try to, in order to understand what's going on here. You see the election is happened And then you see the term is one here. Maybe you can do something like just stop this leader. Then one of the followers, you see they are all have random timeout here. Oh, no, not stop. Sorry for that. Resume. Let me restart it. Okay. You see, yeah, just became a leader, and you can see this is a simulation of Raft, typical Raft consensus within a cluster. That a client gets an ACK back to that the operation succeeded, only then for another leader to come to roll back that operation. Yeah. Okay. So I just wanted to show an example in the code base. So I just make a research what goes with the implementation in different languages. I'm trying to implement a project by using Golang, but I just wanted to show something in the Kotlin, why what they have written actually. So in this project, I just fetch from GitHub Raft Kotlin, somebody written text, whoever it is. And then you see there's a Raft implementation, and it just provided a key value example. So what I would like to see is their usage. This is the consumer of Raft Consensus. And within the key value, this is a component. And within this component, you can see that there is two endpoints, get and post endpoints to the typical, let's say that API interface. You can get data by key, or you can put data into this key, typical map implementation. So the data exists in the payload, request payload. So what happens here? If I am a leader, I am applying this command. Think about this log, think about the state machine, that we will see the implementation of this part, and respond to the client side, right? If I am not a leader, think about this. I am returning to the client saying that, oh, there is a temporary redirection. So think about this. You are trying to access a URL. Instead of providing a 404, you can just provide a location header so that client will know that what will be the next possible redirection URL to access there. We are saying temporary redirect because this is a node, but this can be a typical next leader. So we are not saying that permanent redirect. If you do that, the client will continues to try to connect this leader host. But keep in mind that this can be a temporary leader. But anyway, this leader host, so we already know there is a node implementation. And with every node implementation, there are a couple of domain functions. So you can know a couple of information. Who is the leader? If I am a leader or not, as you can see, node is leader. So this running small servers or API interface lives within the entire nodes in the cluster. So I just receive the payload and try to apply the command. Same way, if I try to get some data by key, I need to, if I am a leader, I need to access my state and get the key. And that's it, respond the data. Otherwise, I need to respond this location here. And let me try to show a couple of examples within the nodes. So we are talking about nodes, but what are they nodes actually, right? Raft node here. So you see in the Raft node, there are a couple of dependencies, something like we are trying to create a controller. There's a controller here, and this controller is formed up a configuration, environment configuration. Let's say that it can be something like maybe database URL, database location. I have mentioned about BoltDB, and maybe it can be the information about the path of the database file. And you need to provide your IP address or host name or whatever it is to do this controller so that it will know the IP addresses. And then as the init function, we are providing this start. So we will have a look at this one. And you see there's a get state actually to access the actual log. You can do that. The utility function that's saying that if I am a leader or not. you see there is an enum function, and my current state is equal to leader, then I am a leader. I am saying this one. And there is an apply command. Let's have a look at this part, start. So what is this? What is this actually? So think about that. You have 5 members. When you start this application within these 5 members, you will see this block will start to execute. Here, for example, there is prepare term increment subscriber. This is typical voting operation, right? You see it is asking for vote. It increments term by 1, which is next term. And if the result is correct, it promotes itself to the leader. So this is for leader selection. So why there is some kind of coroutine here? Because the followers, let me try to go back into controller here. No, not controller. Yeah, this start function. Okay, because in every kind of node, they can be follower, they can be candidate. Within this same separate thread, this logic should always work. If I get a heartbeat timeout, then I needed to be able to just initiate the candidate selection, right? This is for it. And what about this heartbeat timer? Here, what we do is, if I am a leader, we can see the implementation of heartbeat send. If I am a leader, I continuously send heartbeat to the followers. That is the main logic here. When you open this one, if I am the leader, what I do is I just continuously send the heartbeat message to the followers. So heartbeat does not mean just only ping. If you have some kind of data, it is just appended into request payload, and it is sent to the followers. You see, we are trying to send this one, broadcast this one to the entire followers. And what is next here in the Raft controller? Prepare hard timer, subscriber. Yeah, so within the append entries, you see append entries means there is a new data, or there might not be a new data. Just get this request and try to save it into the logs, and then after that into the state machine. Let's have a look at this data. I mean, what does append request means? You see there is prevlog log index, leader commit, so count entries, and also there should be some data. Let me try to find it. Not this one. Okay. Yeah, this one. It is coming from the apply command. So in the apply command, you just do, while you are saving this data to your log, you just, there's a log entry, because you are trying to append entries, and it should be the log actually. And then when you try to, state, here you just set your term. We already mentioned that in a typical log, there should be a term, because you define your selection time, let's say that, term, and you provide your actual data here, the command. So inside the command, you may have different kind of, so we are saying that log state, but when you say to byte, it can be a data for key value database, for example. It can be some kind of message for queue, whatever you have. So this part, this implementation part, is really depends on the actual author. So when you try to analyze the other implementation, you will see there are different kind of logics. If you check etcd Raft, for example, you will see something different. Writing the log message, writing data into the log message and into state machine, it is very general, but there should be some extra logic, because Raft Consensus itself, it's not meaningful itself, but you need to put something extra on top of this. So this was the sample implementation, and there is no other start I can Yeah, most of the time there is this kind of implementation. What I do in the normal life is I just use the gRPC communication for this kind of projects. And then if there is a Raft implementation, I directly use this. For example, I use Go Raft, and in Java, there are a couple of alternatives. I try to provide the RPC interface because there is a contract between servers and clients. And if you define your gRPC contract with the protocol buffers, there's a typical protofiles within this project. And then I generate my stubs by using this proto compiler. And then I use these generated files in the server in order to maintain data. And I also use same files in the client side in order to know my contract. I am about to send the data, but what is the contract? Okay, you don't need to memorize it. There's a stub. You can just include it as a dependency and use it. That is very useful to me to implement this kind of projects. There was a final question about what wrong is in the eye of the beholder. So it is possible that the client get an egg back that the operation succeeded, only then for another leader to come to roll back that operation. So think about this. When you try to access data, you can introduce a strategy. So you are saying that you are connected to the leader, right? So you remember this inconsistent data. Let's say that there is a network partition problem. And within one of the partition, there was a leader election. They try to put some data in a wrong state, but they are minimum set of the network partition. But the actual live part is working correctly. So client is connected to this leader, not the next one. I mean, this guarantees the consistency of the data. That's how this operation works. Of course, there can be lots of edge cases for this. Well, how can we solve this problem? You can do something like, whenever you put something, when you get a response, you have last commit index, right? You can persist this data on the client side, and then you can guarantee that you can guarantee that on the client side, you have the last index. If you get some inconsistent data, then you can just compare. When you get this kind of inconsistency in a time that if you try to read data from followers also, you can get inconsistent data. But if you trust on the leader, then most probably there will be no inconsistent data, because when we say leader, it is the correct leader, not the partitioned and the corrupted leader. So and that was it on my side. If you have any other question, I can happily answer.
So no more questions in the chat?
Yeah, maybe let me check. Maybe we missed something.
Oh, there's a question.
So there was one we just missed, I think. Does this concept mean that writing can only done on the leader? Wouldn't that make a leader a bottleneck on the write-heavy operations? This is a good question, but think about this. So normally you just do something like this. I mean, you send the command to the leader, and then leader does this operation on the background, right? And of course, it can overload the leader. There can be such a situation. But if the leader crashes, then Raft provides guarantee this fault tolerant. I mean, the new leader will be available soon. And this has one outcome. in your client side, you will have a proper retry mechanism. Without the proper retry mechanism, your system will crash because client will not be able to send data or get some response from leader, and it will act like, okay, the system failure, I'm quit. That is a wrong behavior. You need to introduce a retry mechanism on the client side, and you need to expect leader can crash on this part. And we are not doing heavy operations here. We are putting data into log, which is very fast, and you are doing some kind of minimum implementation, putting data into map, maybe putting data into queue, this kind of things. If there is a heavy operation, you need to delegate this one to some other API, not all the logic inside the leader. So you just send a request, and within the leader, it tries to charge customer credit card over Stripe, for example. You cannot do that because it should be something minimum. So this corrupted leader and the real leader, you should have up-to-date term on this part. Most probably this kind of leaders has lower term. So we always compare the term plus the commit index. This is the case. So I try to connect a leader, or I just wanted to become a leader. Okay, I am saying that I am leader. Then if I try to send something to a follower, at that time, if the follower has higher index, then follower say that, oh, I rejected your command. I cannot apply any log coming from you. Then at that time, the follower leader will be decommissioned to the follower state. So the check is handled by leader and the followers at the same time. Mm-hmm. Mm-hmm. Yes. Mm-hmm. For the split brain situations, I think that is the tricky part, but I don't really have an answer on that part. I mean, yeah. So this is the tricky part of this system. So most probably you need to come up with an external check for this. Somehow you need to have a system or monitoring system to prevent this kind of split brains. But at the end, if the entire system is able to recover itself from this kind of operation, then there will be no problem. So if the clients are connected to leader, so there cannot be a situation you connect half of the client connect to one leader and half of the client connect to new leader. So this leader connection is the custom implementation of the authors like us. So how can you connect a leader? So let's say that there is a new leader, but all of your clients are connected to original leader. Let's say that you introduce a new client, just spin up a new consumer, typical client, right? And they may end up with connecting the new leader, but how? There is a split brain there. That means there can be a network partition. But if your client is in the correct network, they cannot connect to a leader exists in the partitioned problematic part of the network. They all should be connected to the correct one, correct leader. So you can have lots of edge cases like this, but you will end up with a situation something like it is not the responsibility of the Raft Consensus. So we are all talking about the IPs, leaders, who is the leader, etc. But they are all IPs or host names, and they are handled by the implementers, not Raft Consensus itself. By the way, recently I started to search for documentations or use case that somebody trying to fake Raft, because it's been something like 8 years, maybe more than 8 years, and they all like Raft Consensus protocol. But I am trying to see who is hardening the Raft protocol so that they will say that, oh, this is another Paxos, something like this. So I am also interested on that part too. Okay. And thank you all for your time, and thank you for listening me. And yeah. I wish all of you have a great day then.